Final topic in our section about equilibrium calculations is a way that we can relate the equilibrium constant to the Gibbs free energy. And I know this is going to sound a little bit like clickbait. Scientists want you to know this one cool trick to relate equilibrium constant and delta G. But I promise that everything in this video is in fact true, and this is not an internet scam. Okay, so here's our cool trick. We have spent the last chapter before this one talking about standard delta G, the standard change in Gibbs free energy, and it let us find if something was spontaneous, which was a really cool and useful thing to be able to do. But remember that because this is a standard number, we can only find whether something is spontaneous at standard conditions, which is one very specific, not very realistic condition. If you were to ask, where would I find the standard condition, the answer would not be inside the human body, on a normal day outside, or in any place that isn't at sea level. So this is only semi-useful, and we would really, really like to be able to find a non-standard version of this variable. So delta G dot is only cool at standard conditions, but not very realistic. So being able to find delta G is actually a very cool trick. So we can use Q from our equilibrium chapter to find delta G, non-standard. We'll put an exclamation point because it's a cool trick. Okay, it's been a few videos since our chapter on thermodynamics. So let's reach way back in our brain and remember about the standard conditions. So we said if we are going to use the sacred tiny zero for standard conditions, we were going to do 1 bar, which is approximately 1 atmosphere, and 1 molarity for all of the items in consideration. They were all in their standard states. And we can assume that they're at 0 degrees Celsius. Not an official part of the definition, but they're usually reported at that temperature. So this is a pretty limiting set of conditions, and we would really like to know things about like what happens inside of your body, where definitely nothing is at 1 molar and definitely not at 0 degrees Celsius. So there is a long derivation that relates Q and delta G together, and I will spare you the pain. If you are interested, it is in your textbook, but it results in the following relationship. Delta G equals delta G standard plus R times T times natural log of Q. I'm not going to do a cool mnemonic device for this one because there's too many G's and I don't know any words that start with Q. So you'll just have to remember. All right, and for the R, we're going to specifically be using the R constant with the joules in it, the 8.314 joules per mole Kelvin. So we've got our constant. This is our standard condition. So we're going to take our standard value. We're going to factor in the temperature and the different concentrations, and we're going to adjust it for the current conditions. And that adjustment is going to give us our non-standard delta G, which is pretty awesome, pretty useful trick. And since we're talking about that cool trick, we might as well talk about another cool trick that follows from the same formula. And that cool trick is that we know at equilibrium that some of these variables change. We know that delta G non-standard is going to be equal to 0 at equilibrium. And we know that for the Q value, Q is going to equal K at equilibrium. So we can use these two pieces of information about our two different systems and use them to adapt this formula to represent equilibrium conditions. So let's write that again, and let's make our changes here. So let's substitute in that stuff that we just wrote about delta G and Q. So we can substitute 0 in for delta G non-standard. That goes away. And we can substitute in K for Q. And then we can rearrange it so it doesn't look so lopsided. Delta G naught equals negative RT ln K. Another cool trick. And what's cool about this is that we can find the equilibrium constant using standard delta G data from the reference tables we were using in the last chapter. So we can use standard change in G to find K, or the other way, or we can use K to find delta G. And this is really useful. It can be really difficult to solve for some of these numbers. It takes a long time. It takes a lot of precise measurements and peer review. And so if you can relate this system of thinking about thermodynamics to this system of thinking, equilibrium, you have just related two worlds. It's like opening a wormhole into a different world. Okay, maybe it's not quite that cool, but it's still cool. It's like the Rosetta Stone of translating thermodynamics into equilibrium. So let's do an example of how to plug and chug into that formula. All right, here's our example. Find the equilibrium constant at 25 degrees using thermodynamic data. So you're going to recognize when you're going to need this formula because you're going to have a super duper empty type of problem. You're not going to have any of the information that you usually need to solve for K, concentrations, pressures, anything. All we have is the balanced equation and a reference table. So we know if we don't have any of the tools we need to solve for K, that we are going to need to solve for delta G and use that to translate into the language of equilibrium. And so remember that we can find delta G total from taking delta G of products minus delta G naught of reactants from that thermodynamic data. And I happen to have a textbook next to me, and so I will do you the honor of looking up these numbers for you. You are welcome. So products is going to be N2O4. And our reactants, of which there are two, it's going to be NO2. We look these up in the table and we make sure that we're looking in the delta G column and not delta H or delta S. And we will find positive 99.8 kilojoules per mole. And we will find 51.30. I feel like I just live on the nitrogen page of the thermodynamic data page. I have it bookmarked in my textbook. All right, math happens here. Add, subtract, and we get negative 2.8 kilojoules per mole. And since I know I'm going to need to use that R constant that's in joules, I'm just going to go ahead and convert that while I'm here. Negative 2,800 joules per mole. And then, since I'm in the business of understanding what these numbers actually mean, if my delta G naught total is a negative number, it's less than 0, I remember that that means that this reaction is going to be spontaneous. Not what the question wanted to know, but still a cool and relevant piece of information. So we're just going to stick it in there. Okay, now we're going to gear up with our new formula. Negative delta G standard equals R times T times natural log of K. We're going to plug in that delta G total that we slaved away for from the reference table. negative 2,800 joules per mole equals negative the R constant, 8.314 joules per mole Kelvin. Plug in our temperature in Kelvin, so 25 degrees plus 273.15 is 298.15 Kelvin, and then times natural log of K, which we are trying to find. Let's simplify, move all those numbers to one side, so natural log of K equals, math happens here, you should get 1.13. And then we will do this just because I'm not sure that we've formally had to undo a natural log in a lecture video yet. We need to undo this log. And the way we undo a log is we take the base, which in this case is E for natural log, and we raise everything, both sides, to that power. So we take E to the natural log of K, and we take E to the 1.13. If this math does not sound familiar, have yourself a visit to the Center for Academic Success. So exponent and natural log base E cancel each other out, and we end up with K equals E to the 1.13, and that number is going to be 3.10. There's our answer. And while we're here, let's observe what we know about K. We know that the tipping point for K is at 1. And if K is greater than 1, that means that the products are going to be favored. There are going to be more products than reactants when we reach equilibrium. Cool. Put a little divider here. So let's look at those fun facts that we found along the way. We observed that we had a negative delta G, and that told us it was spontaneous. And we observed that we have a positive value for K, because it's always positive, and that it was greater than 1, which meant the products were favored. So these two variables are tied together, and they kind of tell different versions of the same story. So let's make that explicit. Let's look at that a little bit more closely. So we said in this case, we had a delta G naught that was less than 0, and we had a K value that was greater than 1. And this told us that we were moving in the forward direction. So spontaneous was talking about the forward direction, so we were favoring going from NO2 to N2O4. We were pushing in this direction spontaneously, and the K value told us that we were going to be pushing in this direction towards the products with our shift. So we can interpret this as products are favored at equilibrium, or forward reaction spontaneous. And we should really put in headers on this table because I don't want to be lazy. So our header is going to be delta G naught over the first column, K over the second column, and information about equilibrium in the third column. Okay, that was cool. Ooh, didn't finish my parenthesis there. Now that's cool. So let's think about what would happen if we were the other way, without actually solving for anything. So if delta G was positive, can we predict what K would be if delta G was positive? So this is how they're related. Delta G naught equals negative RT natural log of K. And if delta G is going to be a positive number, then this side of the equation is going to be a negative number because there's a negative sign. So this K needs to be a small number, needs to be a number that's less than 1, because we need to have something negative times that negative sign to give us a positive delta G. This is that qualitative math we did in the last chapter. So if we have delta G not greater than 0, that means it's non-spontaneous. And if we have K less than 1, that means that at equilibrium, the reactants are favored. So let's collect that here. These two are tied together. There are more reactants than products at equilibrium, and the back reaction towards the reactants is the favored one. The reverse reaction is the spontaneous one. Okay. Check. And the third set of conditions that we haven't thought about is what happens when one of them equals 0. So when delta G not equals 0, this term has to equal 0. And the way that we can make a natural log of something equal to 0 is when that thing inside the natural log is equal to 1. That's just how math works. And so we know that when K is equal to 1, the equilibrium has equal amounts of reactants and products, or at least relatively close. And when delta G naught is equal to 0, we are also at equilibrium. So this one is the reactants and products are present at equilibrium. So in a way, this world of thermodynamics, language of thermodynamics, hold on, I can't spell and talk, thermodynamics, okay. So the language of thermodynamics and the language of equilibrium are really giving us information about the same thing. They're just two different languages telling us the same information. So that was our one cool trick relating the equilibrium constant to the Gibbs free energy, and that is the end of the equilibrium chapter.